Hello everyone, welcome to this 21st lecture in the NPTEL course on Riemannian geometry. So let me remind you of where we are at. So as usual we consider a Riemannian manifold M comma G, and then we consider the unique Levi-Civita connection on it. The Levi-Civita connection gives rise to the Riemann curvature endomorphism and the Riemann curvature tensor. So this is basically a 1,3 tensor, and Rm is basically a 0,4 tensor obtained from R by simply lowering one of the indices using the metric, right. And essentially these curvature tensors measure the lack of commutativity of the covariant derivative, right. So then in the previous lecture we studied some important properties of these tensors, namely we had the following three classes of properties. One was symmetries. So in terms of the local components of Rm, they basically look like the following. So if you interchange I and j, that incurs a negative sign. Then if you interchange similarly k and l, that incurs again a negative sign. So it's skew symmetric in the first two entries and skew symmetric in the final two entries. And then if you swap the first two entries with the final two entries, that your curvature tensor is actually symmetric under this operation, right. And then we had the algebraic Bianchi identity, which basically says that if you look at the first three indices and cycle through them and add up the resulting components of your curvature tensor, then that gives you 0. And finally we talked about the differential Bianchi identity, which said that if you take the covariant derivative of your curvature tensor in the a direction and then again sort of cycle through a and the first two indices of your curvature tensor, add all of those up, you will still get 0, right. So this is the so called differential Bianchi identity. Okay, and one thing to remind you is the proofs depended on doing calculations using normal coordinates. Right, just to remind you, these are coordinates where at that point this is the Euclidean metric and the derivatives of the metric components all vanish, but again it happens only at that point. Okay, right. So today we want to look at a few other nice properties of the curvature tensor, and then I also want to calculate the curvature tensor for our model Riemannian manifolds. So till now the only curvature tensor I have calculated is that of the Euclidean space, because there as I explained the curvature vanishes identically, and this is essentially just a fancy version of Clairaut's theorem on the equality of mixed partial derivatives that we will all learn about in a multivariable course. Using the fact that in the Euclidean space the curvature tensor vanishes, and using the naturality of the Riemannian curvature tensor, we also concluded that the flat tori that we constructed a while back, they all have 0 curvature, right, because they have a local isometry to, I mean there is a local isometry from Rn to these flat tori. Okay, so the first thing I want to talk about in this lecture is are basically commutation formulae. So these are useful in doing calculations. Okay, so here's the proposition. So suppose in some local coordinates I have a vector field that looks like xl dl, and let us say so this is some local vector field, and I have a local form that has this expression. Where x1 up to xn are some coordinates, not necessarily normal, just some coordinates on this neighborhood U. Then we have the following commutation formulae. So if you calculate the commutator of the covariant derivatives in the I and the j direction on x and look at its lth component, then this is simply going to be r I j k l times xk. Okay, and the second point is that if you calculate the this commutator applied to alpha and look at its kth component, then that is again going to be in terms of the curvature, but now there is a negative sign r I j k l alpha l. Okay. So one thing to note, let me write that as a remark, that the LHS in both the cases involves two derivatives. Okay. While RHS is a 0th order term. Right, that is involves no derivatives. Okay, so this is another so of course in Rn, if we had computed this commutator, one would have had identically 0 on the right hand side, right. So so this is again this proposition is a part of this general philosophy that Riemannian geometry is basically Euclidean geometry plus some lower order correction terms. So here when you are applying this commutator on these vector fields and forms, you do not quite get 0, but you get a result that does not involve any I mean firstly it does not involve any second derivatives, it does not even involve any first derivatives. So the resultant is a 0th order term. This sort of I mean these sorts of formulae play a very important role in Riemannian geometry. So I do not think in this course I will have time to discuss the Bochner formula, but that plays an important role in applying Riemannian geometry to obtain topological results, and that those sorts of things depend on such commutation formulae. Okay. Alright, so what is the proof of this? This is essentially, I mean this follows from the definition. So for the first part, this is really by definition if you look at R of del I del j applied to this vector field x, then by definition this is just r I j k l times x k times dl, right. Okay. But on the other hand, I mean this is how we defined these components r I j k l, right. But on the other hand, by the definition of the curvature endomorphism, this is precisely this commutator applied to x minus a term that comes from the Lie bracket term, but this is 0 because del I and del j being sort of basis vectors coming from coordinates, their Lie bracket is 0, right. So so now we just compute what this is. So right, so r I j k l is precisely times xl is precisely the sorry. So R I j k L x k is precisely the lth component of this commutator, which our notation for such things is this, right. By notation, this is the lth component of the commutator applied to x, and so then we have what we had claimed in the first part of the proposition. Alright, so how do you prove the second part? So for the second part, let us compute the commutator on alpha k. What I am going to do is, I already know how to calculate this commutator on vector fields. So using my sharp operator, I am going to go from a one form to a vector field. So this is the same as this applied to GKL times XL, okay. But now, because the covariant derivatives of the Riemannian metric is 0, this is as I had explained a couple of lectures back, that this is equivalent to the metric compatibility of our Levi-Civita connection. One can factor out these metric components out of the commutator. So this is just going to be GKL times this, but by the first part, that is R I j m L times xm, right. But if you now look at these two terms, that is like I am lowering the index of the curvature endomorphism. So that is going to be R I j m k xm, which I want to now switch the role of m and k. So this is going to be R I j k m, but with a negative sign, times xm. But in terms of the curvature endomorphism, this is precisely R I j k upper L times G L m times xm, right. So this is the same as minus R I j k L G L m times xm, but this is the same as minus R I j k L times alpha L. So this is what I had claimed in the proposition. So if you go back to the statement of the proposition, that is what we wanted to prove, right. Okay. All right. So so more generally, for arbitrary tensors, one has the following. So let me write it here, proposition. So let T be a arbitrary tensor of the type AB, such that locally let us say T is going to be given by T L1 up to T LA and T K1 up to T KB times the standard right. Then we have similar commutation formulae. So if you calculate the commutator of nabla I nabla j acting on T, then the L1 LA K1 KB component is firstly is given in terms of the curvature tensor in the following way. So it is a generalization of these formulae that we have for vector fields and forms. So whenever you have the contravariant indices, you get a plus curvature term. So this is going to be of the form summation S going from 1 to A R I j k, you pull out an LS T of L1 up to LS minus 1. Wherever you had LS, you put a K, LS plus 1 etc. up to LA, and then of course K1 up to KB. So you sum over whatever are the repeated indices. So here K is the repeated index, so you sum over all possibilities for K. And then you also have to look at the covariant part of the tensor. So the indices that are denoted by K1 to KB, so they will correspond to the curvature terms showing up with the negative sign. So here S is from 1 to B now, R I j k s L T, the contravariant indices remain the same, the covariant indices you have K1 up to Ks minus 1, wherever you have pulled out a Ks, so wherever there was a Ks you put an L, Ks plus 1 etc. up to Kb. Okay, and once again in this case L is repeated, so you sum over all possibilities of L. Okay, so this is a general commutation formula for tensors. Okay, so maybe the next thing I want to talk about is the curvature of model spaces. Okay, so for the real number kappa, so this is the Greek letter kappa, we said the following. So the space mk m kappa g kappa is going to be the following. So so this is going to be the round sphere of radius 1 by square root of kappa with the corresponding metric. Whenever kappa is positive, it is going to be the Euclidean space when kappa is 0, and it is going to be the hyperbolic space with radius 1 by square root of minus kappa and the corresponding hyperbolic metric whenever kappa is negative. Okay. So then one has a nice formula for calculating the curvature of these manifolds. So proposition the curvature tensor so maybe I should say that these are the sort of model spaces of dimension n. Okay. So these are called the model spaces, or later on we will also call them space forms. or more precisely simply connected space forms of dimension n. Okay, so for now forget about the terminology space forms. I'll just call them model spaces. Okay. So one of the reasons they are called model spaces will be clear in the next lecture when we or maybe a couple of lectures down the line when we discuss sectional curvature. But one of the nice things about these model spaces is that their curvature tensor has an explicit formula. So their curvature tensor is given by R ijkl is this kappa times GIL GJK minus GIK GJL. Okay, so in terms of the metric components, it is given precisely by this. Okay. For any choice of coordinates. Okay, so in order to do this calculation, I am going to recall this lemma from last time. From the previous lecture. That if x1 up to xn are normal coordinates at P, then you had the following explicit formula for the curvature tensor at the point P, namely it was given by del square G I K with respect to del xj del xl plus d squared G J L by dxi dxk minus del squared G I L by del xj del xk minus del squared G J K by this. Okay, all of this evaluated at the point P. Yeah. So I am going to use this formula again. Okay, so let's do the proof of the proposition. Firstly, when kappa is equal to 0, nothing to prove. Since Rm is identically 0, right, on Euclidean space, we have already established that. So let us first assume that kappa is positive. Let us put kappa to be 1 by r squared. Okay. So then the space I am looking at is really this space. Okay. So I want to compute the curvature tensor of this. So let us draw a picture of a sphere. So this is a sphere of radius r, and let us try to calculate the curvature at the north pole. So the first claim is that it is enough to calculate the curvature at one point. Say the north pole. Okay. Why is that? That is because the isometry group acts transitively and also isotropically. Right. So if you can calculate the curvature, so the sphere is a highly symmetric object. So if you calculate the curvature at the north pole, that is good enough. Okay. All right. So so that's what I am going to do. So around the north pole, notice that the sphere can be thought of as a graph of a certain function, right. So one can take the sphere to be the graph of the function where the n plus first component is given by 1 minus x1 squared etc. minus xn squared. So in fact on the entire northern hemisphere you can write the sphere as a graph. So then one can use this to calculate what the metric coefficients should be, so that at the north pole one can easily compute the metric coefficients. So this is simply del by del xi, del by del xj, where I and j now range from 1 to n, right. So these are just the Euclidean components in the in basically the plane Rn that is passing through the equator, right, of your sphere Sn. So using the coordinates on that plane you can write the sphere as a graph, and so then one can try to write the metric components in this coordinate system. So so this is precisely dx1 squared etc. up to dxn squared plus dxn plus 1 squared, right, because you are restricting the Euclidean metric. But what is dxn plus 1? That is given in terms of the other components, right. So one can do this calculation, and I will just tell you what you get in the end. It is a good calculation to for you to write down if you have not done this before. So you get something like delta ij plus xi xj divided by r squared minus summation xi, sorry, this should not be a 1, this should be r squared, okay, times dxi tensor dxj. Okay. So now the thing to note about this formula is that if you evaluate this at the north pole, this is simply delta ij. So sorry, I should say that at any x you have this formula. So now remember the north pole corresponds to the point where x1 is 0, x2 is 0 etc. and xn is 0. Okay. So that means if you plug in xi and xj equal to 0, then the metric at the north pole is precisely the Euclidean metric. Similarly, now if you take a derivative, because these are these depend quadratically on x, an easy calculation shows that if you take the derivative with respect to any xk and then plug in 0 which corresponds to the north pole, then all of these are 0. So that means that these graph coordinates actually are normal coordinates at the north pole. Okay. So then I can apply my formula from before. So then the formula from the lemma, it involves a little calculation. Shows that Rijkl at the north pole is given precisely by r to the minus 2 times delta IL delta JK minus delta IK delta JL. Okay, but at the north pole this is the same as okay. So we have verified the formula at the north pole in these special normal coordinates, but the thing to notice, this is not completely obvious at first glance, so one has to think a little bit about it, that this quantity is also tensorial, and because of that it does not matter which coordinate system you verify this this relationship in. If you have done it in normal coordinates, that means that this holds in all coordinate systems. Okay, so that proves the formula for the case when kappa is positive. Let me just quickly also indicate what you do when kappa is negative. You can do something similar. So so in this case we are looking at the hyperbolic space. So the hyperboloid, the picture is something like this. Again you have a special point whose coordinates are given by 0, 0, etc. up to r. Oh, I think at various points so maybe I should go back and say that the north pole has component 0, 0 up to r, right? Okay. Right. So in this case one can again write the hyperboloid as a graph over the x1 xn coordinates in the Rn plane sitting inside Rn plus 1, and again you can write this as a graph of the following function. Okay. So then again one can do a similar sort of calculation and end up in these graph coordinates with the following function for the metric components. In this case it turns out to be delta ij minus xi xj. So it is very similar looking to the case of the sphere, divided by r squared plus summation xi squared dxi, right. So gij is given by this. So again they are basically normal coordinates. So at P x is 0, so gij at P is precisely delta ij, and you can again compute the derivatives. They are 0 for all ijk. Then again use the formula in the lemma that basically proves that Rijkl at this point P is given by minus 1 by r squared. Sorry, I should have said that kappa is minus r to the minus 2 in this case. So then you have this formula. Okay. Alright, so the moral of the story is that using the formula for the curvature tensor in normal coordinates, one can actually write down the curvature tensor for these model spaces. Alright, so in the next lecture I will explore what zero curvature looks like. So far as curvature has been mostly an analytic thing, it measures the lack of commutativity of derivatives, but in the next lecture I will give at least for zero curvature I will give it a more geometric flavor. Alright, so that is it for this lecture. Thank you for your attention, and I will see you next for the next lecture. Thanks.